There we go. Question.
One function. Like, it's so much harder.
Yes, Davis.
Fall 2021 exam 2 question 5. Started easier. Yeah, based on something. Yeah.
Okay, so this is the one about where the V is vector space of n by n matrices.
Yes.
So this is number 5. All 39. So the question says V is vector space consisting of all n by n matrices. So every vector in this vector space is just an n by n matrix, all right, with real entries. We say the trace of A is in V. So if A is some n by n matrix, we say the trace of the or of A, so trace A is the sum of the diagonals. So if, just so we're clear on this. So if A is this, then the trace of A is just what you get when you add up all the diagonals. So just take everything along the diagonal and add it up. Everybody okay with it? So let S be the set of all matrices. So S is so take out of this vector space of all the n by n matrices, take all the ones that have trace 0. I claim this is a subset. Okay, this is what urges points the problem. What is the burden for us? What do we have to show it's subspace? Got to have a 0 in there, right? Whatever the appropriate 0 is. What else?
Scalar multiplication.
Scalar multiplication and right. Got to be closed under addition. Got to be closed under scalar multiplication, and that's 0. So this, how many do you think this problem is intimidating? It's words, right? Don't let it bother you. Don't. Let's kind of just sort through this piece by piece. What is the 0 element of this vector space? What n by n matrix can you add to every other n by n matrix and it leaves it alone? Well, the zero matrix, right? So. Yes. Think it's zero. Because that's the matrix you need to add any other matrix and it leaves it alone, right? I'm gonna call this Z for zero. Now tell me, my loyal minions, what is trace of Z? I mean, you add anything up to this matrix at zero, no problem, right? Add the diagonals, they're all zeros, right? So Z, our zero element, is in S. There's the first thing. Right? What else we gotta show? We gotta show that when you add two things that have zero trace, you get something with zero trace, right? Well, this is not hard, but I've got to write a bunch of crap down. So for A and B is equal to B from one, B from two, and okay. These things both live in S, right? So what's true? If A lives in S, then its trace is zero, right? Which is what? A11 plus A22 plus all the way up to A. That diagonalizes up to zero. Agree? I agree with that. Now, somebody explain to me, what is the matrix A plus B? Add up the separately, right? So A11 plus B11, A12 plus B12, A110 plus B110, A21 plus B21, A22 plus B22, A2N plus B2N, A1, B1, A2, B2, A2N. Right up there. Now, what is the trace of A plus B? What is the trace of this new monstrosity that we have built? It's also zero, isn't it? Because really what it is. But the A's add up to zero. And the B's add up to zero. So now if I have two matrices A and B that have trace zero, there's some that's trace zero, so it's still in that, right? Oh, I'm on a roll now. Right. So the last thing we have to do is what? Show its scalar multiple, close under that. So let's go back to this. I don't even need to think about being. Okay, so what about a constant time today? How do I multiply a matrix by the constant C? I just multiply everything in there. Trace C in. This is C A11 plus C A22 plus C A11, which is C. Let's close them scale multiples. So instead of all things that trace zero, I keep on today. So everybody clear on that? So it's bad, right? Yes, sir.
Why is the trace of A always zero?
Because I said so, because we picked matrices A and B that were in this subspace, right? And the subspace, if you look at the problem, the subset that we're dealing with is the collection of all matrices, n by n matrices with trace zero. So I'm picking A and B out of that set. So by assumption, they have to have trace zero. Is that okay? Yes.
So, for that question, would we have to show you the different matrices that you just drew out? Or how would we answer that if we were to do that? Because that would take a lot of time to write all that.
I do this so that maybe you understand, right? You okay with it? Notice the trace. Trace of A is A11, A2, and trace of B is B11, B22, B. Since A plus B consists of sums of entries, trace of A plus B, trace A, trace. Really? And trace CA is C A11, C A12. C times trace. Agree with that? Okay. So notice that if A is all zeros, trace A is zero. If trace A zero. By these above properties. I would consider that perfectly acceptable. It depends on your words, how clear you are. If you show me that you've got the idea, I think you've seen on, here's what I do. I go mean on the quizzes, or at least I tell my grader to, I certainly was like that. Because that's the place for you all to get feedback and learn stuff. My tests are not easier, but I am the kinder, gentler Jim, because I realize that you all only have an hour for it. So communicating with me clearly, you don't have to be super, rigorous. You just have to communicate with me, one person to another, that you know what's going on. Okay. That answer your question? Okay, yes,
We do a three.
same exact, yeah. Okay, yeah, so this is a good one, so let's get on our horses. I'll show you some ways to check this as you go along too, which admittedly you don't have time to do that on the test, right? But hopefully they'll give us a better understanding. Let's see, A is. Like it's here, 305. 102. And 327. By the way, can you tell me what the determinant is? Be -2.
How did you tell just from the?
Use the force. So what's the best thing to expand about? The middle column, right? Because lots of zeros there, right? So actually, the only thing that I have to worry about is this. So it should be, 352. Right, when I move to row and column, but this isn't. Anybody tell me what it is? Yeah. How do I know it's negative? This is the -1. Always got this adjustment factor here. It's -1 plus, what you do is take the row number plus the column number. Right, and 5 is of course odd, so let's say negative. This turns out to be 6, or 6 minus 5 is 1. I'm taking 2, -2. Okay, so let's get down to it. It says find the adjoint, the classical adjoint thing. Everybody agree with that? Yeah. This is the transpose cofactor, right? Where Cij is Ij cofactor. I don't just write that for your explanation. If I were doing this problem, I would literally write that on my test. You know why? Because I screw up numbers. And when I screw up numbers, at least Kuykendall looks back and sees, oh, okay, screwed up some numbers, but this person knew what they were doing. Right? So now I know that you know what the answer is. Now the rest of it's just doing some computations, which is messing that up. It's probably a lesser offense. Right? So got to get the cofactors. I'm gonna do these first. Why am I doing these separately? What is efficient about me doing this here? Why did I break them up like this? That's right. The row and the column add up to evens in all these cases. These will all be pluses, whatever I get. But remember, you have that -1 to the I plus j power. These all add up to i's. So it'll be minus the determinant that you get. Everybody okay with it? Okay, now you asked for this question, so let me know if this, you want me to take a step back or whatever. let's try to go through this. C11, what do? Well, we're working on A here. We nuke the first row and the first column, and we get the determinant of what's left over, right? So that's going to be -4. Everybody cool with that? And you all will be well advised watching me on this, because I can easily screw up. C22, the matrix I get when I nuke second row of the second column are on the corners. So I get 21 minus 15, 6. Okay, C33. Nuke third row, third column. Oh, I like that one. Because what do I get? 0. Okay, C13. That means nuke the first row and the third column. That's going to be 2. C31, nuke the third row and the first column. That's going to be another 0. Everybody okay so far? What we got? The next ones are the ones that have the minus in front of them. So, and I've already put the minuses there. Take care of me. Let's do 1, 2 first. Nuke the first row, second column. And so I'm left with this matrix here. 7 minus 6 is 1. So it'll be -1. C21, second row, first column. So that's going to be 0, -10. So it's minus 10, which is 10. Let's kill the second row, third column. 6 minus 0, so I get -6. And third row, second column. I'm going to get this matrix here. That's going to be 6 minus 5 is 1. Let's see. So classical adjoint of A, let's fill in the numbers. C11 is -4, C22 is 6, C33 is 0, C21, 13 goes down here, and 31 goes up there. And let's see, what do we got? 1, 2, that's here. 2, 1 is there. Comes up here. 2, 3 is -6. And 3, 2 is negative. Okay. Any questions? So there's your classical adjoint of this. It says find A inverse. Anybody remember how to do that? Give me classical adjoint.
Whatever the determinant times.
Right. By the way, I didn't ask this in the problem, but I do know that A is invertible because why? The determinant is not 0. Right? So A inverse is equal to so in this case, this is -1/2. All right. So A inverse. In fact, let me write it a little closer to A. It should be classical adjoint with 1/2 of everything. So -1/2, I should say. So that should be 2 minus 5, 0. 1/2 minus 3, 1/2. and minus 1, 3, 0.
That's correct.
Yes,
How did you find the determinant again? Can you show us how you did that?
yeah. Everybody okay with this? By the way, this is checkable. I just did it in my head, just multiply these matrices to make sure you get identity. Right, I mean, I realize you don't have to do that in the exam usually, but. So the determinant of this. I will expand. About. Actually, I'll do the determinant twice, as a matter of fact. Let's expand about the second column. It's going to be 0 times determinant of, let's see, 1, 2, 7. Let's see, this plus 0 determinant of middle column 3, 5, 7. And finally, minus 2 determinant of 3, 2. Three, 5. You understand that, all right? And of course, I really didn't need to write this down. Right, because there are zeros next to the point. I'm going to say this -2 and 1 is -2. This is yet another kind of example I can give you. Look, let's do it another way. This is a good check. Let's do this the way that we're all used to, right? Let's see, the 3 comes the determinant of 0, 2, 2, 7. Minus 0. Determinant, I don't really care, but I'll let it go with this. 1, 2, 3, 7. Plus 5 comes the determinant of 1, 0, 8. So this is 3 times -4 minus 0 plus 5 times 2. So that's -12 plus 2 is -2. Math takes care of that, right? Check it. Yes. Okay. Oh, I didn't finish your question. I'm sorry about that, but did you have one?
Yeah, I was wondering, oh, okay, so you're able to pick any row or any column to find that?
That's the beauty of it. That's right. As long as you keep track of the minus sign. So for example, if I expanded about this row, so the entry here is the second row, first column. So let's start with the -1 and then it alternates sign. So don't forget that minus sign that alternates. Okay.
So is
Yeah.
is the adjugate just the inverse multiplied by the determinant?
If the determinant is not 0, you can always get an adjective, right? You can always get that. But the answer to your question is yes, if the determinant is not 0. Okay. Let me finish up this one here because I've got all excited, but there's other parts to it. It says, suppose S is a sphere of volume V. So, yeah, it seems like I kind of had a stroke making up the problem, right? Because at first it seems like it's not related. Let's be sphere volume V, some volume. I haven't told you what it is. I'm pretty sure that's a positive number though. What is the volume of TS? Where so A is a 3x3 matrix, right? So that gives you a linear transformation from R3 to R3. And what it's going to do is it's going to take a sphere of some volume here, say X, Y, Z coordinates. Uh, and it's going to turn it into some unholy blob over here. Actually, it won't be that unholy. It'll be some kind of listed ellipsoid, like a football perhaps. Right? And the question is, if this originally has volume V, so I'll measure its volume of V, when I do this linear transformation, what's the volume of the new blob? Right? It is amazing that this linear transformation gives you a nice formula for it. Anybody remember how to do this?
Isn't it volume is that final volume is the absolute value of this.
Good. So let's write it this way. I think this. And by the way, this volume in two-dimensional space could be an area or a length, if it's a one-dimensional vector space, or it can be a five-dimensional volume, any volume you like. Volume new is volume old times the absolute value of the determinant of A, where you have a linear transformation. So we'll see what volume new is. The volume old was V, because that's what the problem said. And the determinant of A is -2. So whatever the sort of linear transformation is, whatever sphere you got, it will just double volume. Yes.
So is the determinant the area of like between the vectors, or is it what is the scale of that?
Well, there's a number of different interpretations of the determinant. So for example, the absolute value of it is, if you look at these three vectors here in three-dimensional space, they'll span sort of, I hesitate to use the word box, because it's not. This is called often a parallelepiped. It's kind of a twisty box, right? It's a box that some person sat on, right? Perhaps a little bit. If these are the three vectors that determine this, take a determinant of the matrix that you make out of those three vectors and take the absolute value of that. Right? And that's essentially what we're doing. Right. So find the value, find any value, so I'm generous there, find any value of lambda such that the linear transformation so this is the kind of practical thing that you might need to do. I mean, you might have to, you're doing something like, is anybody, you guys are probably too young to remember, is anybody ever seen like a TV program on TV with black pixels? And the pixels are too big and it looks like totally coarse. Well, so this is kind of a linear, algebra problem, right? Now suppose that I know that this matrix here, this linear transformation, multi-line matrix, it doubles the volume, right? Maybe it makes my pixels too big. It's not very good for looking at my high definition footline, right? So I want to change this linear transformation. And that's the motivation of this problem. So find any lambda so that the transformation L of B equals lambda A B. Reserved volumes. So in other words, what I want. When I look at this linear transformation, when it turns it into that block, I want this to be volume. Right, so the volume of T of S was twice the volume of the original sphere, right? Notice that the L is almost like T, only I put a scalar there, kind of adjust it. I want to find that scalar so that it leaves the volume alone. Doesn't make it shrink, doesn't make it too big, it leaves it the same. But okay with that? Okay, so how do we do this? Well, I'm just going to use this whole thing again. Volume new, volume old, times determinant of X. Volume new. And this time my matrix is what, lambda. Right? Because I don't have A like I had before, I'm trying to adjust, I'm trying to multiply by lambda. So I want volume new and volume old to be the same, right? I want these both to be B. So what does the absolute value of the determinant have to be? So I want and actually, technically, the problem I said find any value. So let's try it for this. What's the determinant of A? It was -2, right? What are you supposed lambda should be? What was it now? That's what you think. You got to be careful. But the problem is A is a 3x3 matrix. So let me write it this way. Now this is so let me write this way. maybe that'll kind of help us, because what's the determinant of A? This was -2, wasn't it? What's the determinant of this? And the cube. So actually, we can plus or minus. The lambda is. And actually, it could be either plus or minus, because it's the absolute value. Either one of those work. So so that's actually, if you use 1/2, which would not even be the first thing I would think of. Remember, this is just a scalar, it's multiplied out through the matrix. And because, by the way, what are you supposed, so we got like 1 over the cube root of 2, right, to solve this problem. What would have happened if A was a 2x2 matrix with determinant -2? What do you suppose we would have then? If we went over the square root of 2, that's right. What if it was a 1x1 matrix? You get the 1/2, the original naive answer, but the bigger matrices, you've got like a larger determinant here, or more complicated. Any questions? Okay, yes, sir.
Do,
Quiz 11, number 2.
yes.
So consider the matrix B. Let T from R squared be the linear transformation. This linear transformation given by T of X. And multiplication by B. Okay, so the first question is C denotes the unit circle x squared plus y squared is 1. Describe the image of T under of the circle under T. So write an equation for this. Well, here's what happens. You start with the unit circle in the x y plane. These are a bunch of vectors. I'll linear transform the vectors all over here. My new set of coordinates. And all these vectors are going to turn into something new. And I'm going to get some blob over here. This circle's going to turn this. You can actually use it for something like this, right? Find what the equation is. And I'm going to give you kind of an application illustration. So, how do we do this? Well, XY is on circle. For example, this. Then x squared plus y squared is 1. Right? Because that's what all the vectors on this are just x, y, or x squared, y squared, x squared plus y squared. Everybody okay with that? My big question is, what do they turn to after I smash it with this vector B or this matrix B? Well, if you look at 3, 5, 2, 3. You get that. And these are my new coordinates, call them U and V. And I want to figure out what this sucker looks like in my new coordinates, right? What's an equation that governs this in my new plane? Well, let's just naively write this down. And what I want to do is I want to solve for X and Y in terms of U and V. Right? What I'm going to do first, so I'm going to multiply this top one by 2. And I'm going to multiply this one by -3. And my strategy here, of course, is to get rid of the X business. So what do I get after all this rigmarole? I get Y is equal to 2U minus 3. Now I can figure out what X is in terms of this. It doesn't matter which one of these equations. I'll use this one. I'm going to take my newfound knowledge here and replace Y with this thing, right? So B is this garbage. So what I get is 2X is equal to minus 6U plus 10B, I guess. So I get X is minus 3U. Right. Now here's an equation that this thing satisfies. X is this, and Y is this. And also, what do I know about X squared plus Y squared? These are points that came off the circle, right? So these are all equal to 1. Because X, Y, that was a vector that sat right on this unit circle. So this is actually good enough for your purposes. X squared is minus 3U plus 5B squared plus whatever this other one is, 2U minus 3B squared. This is good enough. But just for dramatic purposes, I'm going to multiply this out. That's 13U squared minus 42 UB plus 34 B squared. How many of you recognize this? Notice I didn't raise my hand either. I would have to sit down and muck around with it before I was completely convinced it was ellipse. It is. It's not, I mean, you all are used to ellipses being like X squared over A squared plus Y squared over B squared equals 1, right? You'd have to complete the square. Basically, this is what happened. Somebody took an ordinary ellipse and stretched it out a little bit, and then God, not satisfied with the mess we had made, turned it like this. That's essentially what's happened. So it's an ellipse, not only is it stretched and squished, but it's twisted. Okay, let me ask you this. Would you rather study properties of this or properties of this? Everybody votes the circle, right? For sure, for sure. This answers that question that you were asking me. Why do we want to change coordinates? Because this is essentially the same shape. In these coordinates, bad in these coordinates, good. So if I walked up to you on the street and gave you this thing, what do you want to do? You want to hit this thing with the inverse of that matrix, and it'll turn it into a circle, right? And that's what you, and actually, here's another bonus coming up in this problem as well. It says find the area enclosed by this new curve, right? Well, what's good for volumes is good for areas. So area new is equal to area old times determinant, well, absolute value of the determinant of A. So the new area we want, and this funky ellipse, well, what's the old area? What's the area of the circle? The radius is 1, so the area is pi. Pi times 1 squared, can't beat that with a stick. And what is the determinant of A, which I have conveniently erased, but I think it was -1, right? Wasn't it 3, 5, 2, 3 or something? I think it's fairly clear the area of this is pi, right? Circle. It is not clear the area of this is pi. Linear transformation doesn't. Yes.
So I think we just basically. That up.
That's right, because I didn't want to confuse my notation. I'm calling things X and Y over here. If I also call this X and Y, am I talking about this X that was over here or this new one? And so I changed the coordinate names just so that I can keep up with the bookkeeping, right? At the end of the day, after you solve this, you can rename your coordinates X and Y and redo this, right? But this X and Y is not the same. In fact, this linear transformation changes. And that's what I'm trying to proclaim. Other questions? Right, okay with that? Okay, yes,
Where did you get that determinant? David, what?
yeah, because like an idiot, I erased the original matrix, but let's see here. The original matrix was. Yeah, so there you go. Actually, so I should have said determinant B, because that's what I call the matrix in this problem. Yes. What's the other question?
Yeah, I had some questions.
Oh, okay, gotcha. Okay, others? Yes,
You do number it real same.
3. Consider the upper half of the ellipse, blah, blah, blah. Find the volume obtained in this region is revolved around the x-axis by finding the appropriate linear transformation. And using the fact that the volume is here. Okay. This one requires, there's actually, you can do this. Well, again, with the math and checking here, I'll bring this up at the end. So. This is like x squared over a squared, y squared, b squared. This is probably, how many of you is this more familiar as something else? Maybe seen it in some place. Right. And what do I do? I put a handle on this and I start spinning it around and it makes this football looking thing, right? This is 0b. This is A0, this is negative A0. When I flip it around, or when I spin this around, what's this going to look like? Well, it's going to kind of complete all out here. And you're going to get this kind of solid looking thing. Right? And this length here will be A. And this length here will be B. And then there's a link coming out of the board, right? What will this link be? This will also be big, right? Because we spin it around the x-axis, everybody agree? So basically, the cross section right down the middle is a circle radius b. And the question is what's the volume of this, right? And I'm gonna, so everybody okay with this? We have an ellipsoid A, you can, right? Yes,
I just can't see, does that coordinate, say A0?
yeah.
I just can't see it here.
Okay, everybody with me so far? Now, what I wanna do is, I gave you a hint, the volume of the sphere of radius R is 4/3 power 2. Y'all have all seen that at some point. Right? So let me ask you this. Anybody think linear transformation, I'm gonna make this easier on myself. So can anybody think about the linear transformation? That takes a perfect sphere of radius 1 and turns it into this.
And then you make the set 1, 0, 0, 0, 0, negative starting.
Actually, it's easier than that, right? So you're thinking of kind of rotating something. Oh, and that gets me back to your question. Remind me about your question, didn't I? Imagine these axes are the same. What do I want to do? I want to make X grow. I want to make the X coordinate grow from 1, well, assuming that the appeared 1, but it doesn't matter. I want it from radius 1 to radius B. I want the Y coordinate growing out to A. And the Z coordinate growing out to B as well. What this does is this takes the vector 1, 0, 0, right? So that's 1 unit along the x-axis and stretches it to B 0, 0. So you're stretching B units in the x direction. You're stretching B units out in the. You're also stretching in the Z direction, B units, right? So you're stretching the same amount the X and Z, and you're stretching A units in Y, right? It goes 0, 1, 0 goes to 0, A, 0, right? Everybody okay with that? So basically, it's like this is like a piece of silly thing. You stretch X and Y, same amount up to B, so you get that. And then you stretch Y out to A. Okay. Now, if you believe that this linear transformation does this, and I can show you that it'll turn the circle into a sphere, but here's why this is easier now. Volume of ellipsoid. This is our new thing. It's volume of sphere times the absolute value of the determinant of A. Right. Okay. What's the volume of my sphere here? The original volume, it's got radius 1, so it's 4/3 pi times 1 cubed, right? So this should be 4/3 pi. And tell me, what is the determinant of that matrix that does the stretching? What's that? It is AB squared. So they're just like that. That is, that generalizes the sphere to an ellipsoid like this. By the way, this isn't part of this class, but how could you check this? This should probably be a familiar problem. That's a terrible list. Sorry about that, but y squared, if I solve for this, is b squared times 1 minus x squared equal to a squared. Y'all remember this crap with the is and all? Washers and the discs and all that business. The volume of this should be the integral from 0 to a, double it, 0 to a, it's the 0. Double line from 0 to a should be pi radius squared, which is y squared, dx. Right, that's the old this point, which is 2 pi integral from 0 to a of y squared, b squared, 1 minus x squared over a squared dx. And this is 2 pi b squared integral from 0 to a of 1 minus x squared over a squared dx. Which is 2 pi b squared x minus x cubed over 3a squared, evaluated from 0 to a. And this is a, and this is minus 1/3 a, this is 2/3 a. 4/3 pi a b squared. What we have. Math always takes care of. Any questions? Bobby, can you remind me of the problem that was?
It was 6 on summer 2018.
6 on summer 2018. Okay, so here is well, I gave you this matrix here. I went through the first part of this class. So that was the matrix A. Suppose there's a real number lambda and a non-zero vector such that A be lambda B, so we'll go with this again. Suppose this. And what the problem asks you to do is to show that the determinant of A minus lambda I is 0. Well, so here's the deal. this first part doesn't really have anything to do with what that matrix is. It matters. It only matters if it's a matrix and it's 2 by 2. Suppose that AB lambda and B is not 0. This means that AB minus lambda B is equal to the 0 vector. All right? And I'm dying to pull that B out, pull it in. But as written, explain to me why that's really not kosher. What's wrong with that? That's right. What we have here is we're trying to add up apples and oranges, and it doesn't work. This is a 2 by 2 matrix. This is a number. What does a matrix not? It doesn't make any sense. But this is easily fixable because this is really what's going on, because B times 2 by 2 identity is B, right? And this kind of puts everything balances on level plane. Okay. So what this means is, so B is a non-trivial solution to A minus lambda I to X is equal to 0 vector. Now remember, think of this as just one big fat matrix, because that's what it is. It's a 2 by 2 matrix. 2 by 2 matrix times X, 0 has a non-trivial solution. That means the determinant of this is what? Well, I'm sorry. It's determinant equals. Because it's got a non-trivial solution, so the determinant has to be not 0. If you look at the columns of this, they can't all be new. Or the set of columns can't be. Any questions on this? Okay, now in part B, I actually really do need this matrix because it says for the matrix A, find an equation for lambda if determined if this. So. And I'm gonna start writing out too. Let's kind of work this here. My vector here is there's my A. And there's my lambda I. Agree? And I subtract them, so I get one big fat matrix. Here we have cosine theta minus lambda minus sine theta cosine theta minus. This is in all its glory A minus lambda. Okay, and what do we want? We want the determinants to be 0. So this will give me an equation for lambda. So let's look at that. Well, and let's take the term of this. It's part of these two minus part of these two. See what happens. This is cosine theta minus lambda squared. Cosine squared theta. Right? You multiply this out. So I'm gonna get lambda squared minus 2 cosine theta lambda. What's cosine squared? Theta. Cosine squared. And there's an easier name for this. Can you simplify that? What's cosine squared theta? Cosine squared, right? So I get lambda squared minus 2 cosine theta of lambda plus 1 is equal to 0. And I think that's all that problem is for that particular part. Find an equation for lambda, determine, there you go, there's the equation. For what values of theta is the equation solvable in real numbers? How do we figure that out? How many of you remember the quadratic formula? Add some grammar, maybe. All right, because we're gonna need that here. How many of y'all remember it? We're gonna need this here. How could you tell? There was a square root involved somewhere in there, wasn't there? How do you tell when you got a real solution? When the crap under the square root's not negative, right? So, short review here. You have ax squared bx plus c equals 0. Here we need a not 0, from obvious formula. The next equals negative b plus or minus square root b squared minus 4ac over 2 right. Right? And so we've got problem things. This is the crap that goes into the square root. So 4 real solution need b squared minus 4ac be greater than or equal to 0. Everybody agree with that? Let's apply this to our problem. So the real solution need something greater than or equal to 0. B squared. For this particular problem, what is our B? Negative 2 cosine theta. Do I agree with that? Minus 4. What's my A? A is just 1. It's my particular. Right? And C? Also 1. I agree with that? So I get 4 cosine squared theta minus 4 is greater than 0. So I get cosine squared theta is greater than or equal to 1. Right? Is this ever possible? Oh, sure it is, but it has to be equal. Right? It can't be greater. And where is the cosine of theta? So the cosine of theta, 1 and minus 1. It's got to be one of those two. That's the only way that this holds. Where's the cosine of theta? 1. Zero, 2 pi, and it's -1 at pi. So for those three values of theta. And actually, the 0 and the 2 pi are capital T, so the same matrix. Whatever. Okay. Yeah. Notice I didn't ask you the answer. Yep.
As, so, for 2022, or you got. Question 1, parts H.
I'm sorry, did you say 2021?
2020, well, it's on 2020 and 2022, but,
2022 exam.
H and I exam.
Okay, so let in by compute row A minus 10 col A. Okay. Oh, this is a good one to think about. Yeah, so these should, I hope, be kind of quick, because they're in the short answers part. So for H, we have A and R in by N. And it says compute in row A minus in column A. Yes, it's exactly right. Because the row rank and the column rank are the same, right? The number of linearly independent rows is equal to the number of linear columns. In fact, for this one, you don't even really need that. There to be a square matrix. Because the number of linearly independent rows. So what's the dimension of the column space? It's the number of pivot columns, right? And that is also the dimension of the row space, because the number of pivot columns should equal the number of non-zero rows in the row rank. Right. How about, and the other one is row A minus in column C. What's this one? This is also 0. Because the dimension of the column space is equal to the dimension of the column space. So, but okay. Okay, others. Yes.
Fall 22, question 2. Question 13.
So. By the way, did you get an answer for this? Okay. A, B, and B is so we've got A here. Okay, I'm gonna go through this, yes,
As a linear transformation, what would that do? That rotated on axis, x-axis.
so what it would do is, it takes the vector 1, 0, 0 to a 0. Right, you can't always do what I'm doing here, because sometimes it's hard to see, but this one you can. It stretches the x-axis, right, so the x-axis goes out. In the YZ plane, so if x comes out of the board here, the YZ plane is the plane in the board. So what it does to the YZ plane is it takes a vector and it stretches it by b, and then it rotates it by theta. Right, so it's pulling out, if a is positive, say, then it pulls, it stretches a in this direction out of the board. And in the plane itself, it takes any vector here and stretches it b and then rotates it theta. That's essentially.
So have you used that was the problem?
Could we, you mean the spinning part that I did at the end?
No, like how,
The ellipsoid problem didn't do any spinning, right? It just stretched in all three directions, right? So what's happening here is you're only stretching in the x direction. You're only pulling out of the board. What you're doing in the board is you're stretching and spinning, right? So it's kind of like this is a cadence, right? So imagine what's happening in the board is a two-step process. Take every vector and stretch it. So you expand it and then you rotate it.
I was confused, I used that when I was doing it, and the derivative of that was, same as the other.
It's the same as which?
AB squared.
What do you mean the derivative of
Not
this?
derivative, the determinant of which is the same.
Ah, yeah. So this would do, so. You're right, it does have the same one. It does a spinning action, the other one didn't. The one that I gave you was simpler, because all it did is stretch in all three directions, no spinning. This does some spinning, right? But you're right, he met the determinant of, it's A, so expand about the first row, right? It's A times the determinant of this mass, and then you're done. And the determinant of this mass is b squared, right? Because it's b squared cosine squared plus b squared sine squared, so the determinant of this is AB squared, right? Okay, so I won't get on my horse and ride, and I'm just gonna. So. I'll show you another way to do this. Oh. Actually, I didn't read the problem, it's easier to do. Find A times the classical algebra. So if I asked you to do classical algebra, I mean, how many of you are considering like, leaving and listing in the Peace Corps or something, right? I mean, you're gonna do this, right? But there's an easier way to do this. I didn't say that you had to compute classical algebra A, although it might not be too bad because you've got some zeros in there to help you out. But there's an easier way to do this.
Find the determinant.
In this case, the appropriate n is 3, right? What is the determinant of A? Did everybody follow our logic earlier? That the determinant was AB squared. So here you go. There it is.
Wait, how'd you find the determinant being squared in?
Well, so expand say across the first row, right? It's gonna be A times the determinant of this. And then the rest is zero, so I forget about that.
Yeah.
And so the operative question is, what's the determinant of the little box here? So what I would get is B squared cosine squared theta plus B squared sine squared theta. Right? Pull out B squared and select B squared. Yes.
And how did you know that you could do that? That you could set it equals to determinant A?
That's a formula we actually have in class, like when you multiply a matrix times a classical adjoint. Yeah, so that's actually a good, when you're on the homework, you want to test yourself, you put all this work, some moron asks you to figure out what the classical adjoint is. And so sweating and crying, it takes you forever, and you finally get the thing. One way to test it is multiply it by the original matrix A, that you got it from. If you get a diagonal matrix with determinant down then you win. Yes,
Is that derived from the A inverse equals one?
no, the other way around. The thing you're saying is derived from that. Others. Okay, so what else do we have on the plate? It says find oh, by the way, I did say in this problem that A and B are bigger than 0. Notice that this guarantees that this is an invertible matrix, it's A and B are positive. And so that's why find A inverse. Well, A inverse exists because the determinant's not 0, right? So I'll just, if I don't remember the formula, which I don't off the top of my head, I'll just manipulate it. Multiply both sides by A inverse on the left. That's the identity. So, right. So this right here is, of course, this is the identity matrix, so it doesn't affect anything. So what I get is A P A is equal to A inverse determinant of A. And so let's find A inverse. Right. It's even the way I worded that, I'd probably give full credit for that. I don't know if it's not clear, and I'm angry at myself for this. It's not clear from the problem. If I'm sure somebody must have asked, and I must have told them what to do. Well, let's just find A inverse. Well, there it is. But what if I ask for it for a specific problem? You might figure out what A inverse is. Can you figure that out? We actually did a couple things in class, so wait and see. Anybody know how to do it? Yeah.
I have that thing.
Okay, and where'd you get for A inverse?
It's 1 over A. The
And
cosine theta.
like that?
Yeah,
Theta.
and then the one next to it is a sine theta. And it's basically the same thing. And that one's easy fraction, and that was.
Did I get that right? How did you get that?
Well, I actually did the classical add all that.
Oh, you sort
divided by the.
Yeah. Yeah, you can do it that way. It's clear this needs to be 1 over A, right? one over A becomes congruent one, right? So think of it this way, what you're doing is stretching this dimension, and this is how you do the stretch, right? And now what you've got to do is undo the rotation and the stretch. So what do we do in this thing? We stretched it by B and then we spun it, right? How do we get it the other way around? So I'll show you a quick way to do this. So this is it. This doesn't work in general. This works for this particular matrix. And a lot of these kind of matrices do show up in physical applications. So here's how I would build A inverse. So just a stretch or the contraction in the A direction, right? So pull X out by A, one over A gets you back where you are. Ready? Now, what did we do here? Well, this one, is stretched by B, then rotate by theta, right? We looked at these kind of rotation matrices earlier. So I want to undo the stretch. So I'm going to undo. And I'm going to undo the rotation. And let's switch that. Cosine negative theta. Minus sine negative theta. Sine negative theta. Cosine negative theta. So I've undone the stretch and then I've rotated it back. Right. And cosine is an even function. So cosine of negative theta is theta. And sine of negative theta is negative sine theta. And that's why you get that sine reversal. So 0, 0, 1 over b cosine theta, 1 over b sine theta, minus 1 over b sine theta, 1 over b cosine theta. And that should undo what you did. And see, that's what the cosine squared of the sine squared, that works. And I'm just going to be stuff. And that out of the, but again, you do this with a practical adjoint, you can do some kind of row reduction, there's lots of ways to do this. Yes.
Are you recording,
Yes.
where was, I'm just late for work.
That's fine, yeah, we're recording. Okay. And it looks like it's working, so. Okay, any other questions? Give your boss my old test, I'll shut him up.
I was supposed to be there at 5, but I told them I'd be a couple hours late.
Okay. Okay, other questions? Any?
One of the exams, you just asked us to define a determinant and matrix. It's a good definition. For that is that.
Oh, so I asked you to find what the determinant of a,
And by the matrix, and you can assume that the determinant.
you know, here's what I look like. I mean, there's a lot of ways to do it, like, the definition per se, so. Uh, determinant of M is, minus one, well, actually, no, A11, determinant A times J, 1 minus A12, determinant. Uh, I would just do that. Now, obviously, I'm using determinant, I'm determinant, but this is a recursive definition. If you want to be really complete, you tell me what 2 by 3 determinant is. And the rest is exactly. I mean, I just wanted you to know what it says. There's a lot of different ways to do this. I don't like asking that question, although every once in a while I'm obligated to, because I hate to grade the thing. This was one of the different answers. Yes.
So why do you have n plus?
Because let me put it to you this way. Let me break this out further. And I did leave out part of this definition. Let me write that down too. Because notice the minus sign occurs exactly when that second number is even. Correct? And so if this number is even, I want it to be minus. If this number is odd, I want it to be plus. That's where A1J is matrix obtained by deleting first row and J column. Okay, coming with one ends on it. And yes, I know you can expand on any row or any column, but for definition, that's perfect. Yes.
So like on the ultimate exam, there's a ton of different ones just relating, like asking what the definition of them are. Would it be wrong just to manipulate the adjoint times a for determinant? Just put that as a student.
Okay, so can you be more specific about what you're talking about?
Like number 3 says the classical, how is the classical adjunct? Like could I just say that that's a
We're talking about number 3.
oh C.
Oh, see on number 1 says. Oh, yeah. I'm just looking for this thing right here. A inverse equals 1 every determinant of A. Classical adjoint of A.
Yeah, so I just manipulate that to answer like that question. Like find the try to say that the determinant of A is
That's a good question, but here's the problem. That wouldn't really be right. Because So what you're saying is, determinant of A is equal to A times adjoint A. Classified, correct? That's what you want to do. But this is not true. All right, what's wrong with this? This is a number, this is a matrix. Now, if what you said is that probably gets you some points. If what you had said was the determinant of A is defined to be any diagonal entry in the matrix A times the classical adjoint of A, that's not really a definition, but that would have made me laugh hard enough to give you full credit. So, yeah, I mean-
I put something like that on the practice.
yeah, okay. Yeah, that's not really the way you want to define something, right? Because unfortunately, the classical adjoint is defined in terms of determinant, so it's circular, right?
I also have a question about the A.
Okay,
When you define the cofactor I did. And I don't know what the right is like, because I know it's -1, the IJ, and then there's.
okay, so here's what I would do, so. With that one. IJ cofactor. Cij is -1 the I plus J times determinant of Aij, where Aij is matrix obtained by removing ith row and j column. Yeah, the most common mistake, I would think in this definition, for getting that -1, yeah, that's good. But it's like the cofactor, is you remove the ith row, j column, now you've got an n -1 times n minus 1 negative, so you determine that, multiply by that possible negative sign, -1 to the I plus j power. Good question. Yes.
But it's a question somewhere in 18 that says, suppose you have a set of factors. B1 through K. And spans Rn. What's the relationship between K and that?
Which one is this now?
Example 2 from the 18 part you see. The question.
Okay, so you have B1 up to BK spans. Okay, okay. So like span. Are. What can you say about the relationship? Let me ask you this. Suppose I have Rn. What's the smallest number of vectors that I could hope to have that spans all of Rn? Can I span R3 with one vector? No, there's not. Can I span it with two?
And, that's it.
I need at least three, right? So in Rn, how many vectors do I need? In fact, the smallest spanning set is basis. How big is the basis? In elements. That's the smallest spanning set. Once you've got a spanning set, you can go out and get a bulldozer and shovel and start dumping other vectors there, and it'll still span, all right? So the smallest set of vectors I could ever have, hope to span Rn is in vectors. I've got K of them that span Rn. What do I know about the relationship between K and N? There have to be at least n vectors. By the way, what if I had said this set of vectors is, forget spans, what if I said that set of vectors is a linearly independent set of vectors in Rn? What's the relationship? K is less than or equal to n, right? Because in Rn, the largest linearly independent set you have is n, right? So if it's linearly independent, there could be no more than n. Think of it this way. If this is linearly independent, then what you're doing is you're making this vector, or I'm sorry, making a matrix by putting these vectors in here. That will be an n row by k column matrix, right? For linearly independent, every column has to be a pivot column, right? Which means that the number of columns has to be less than or equal to the number of rows. Makes sense. Yes.
You do full 22, question 1 part K.
Okay, this is a good one. I have a 3x3 matrix A. I shift the bottom 2 rows up. Oh, I shift the bottom 2 rows up 1 level and put the top row at the bottom. What is the relationship between the determinant of this new matrix and the determinant of that? So here I have A. Row 1, row 2, row 3. I get a new matrix B. It says, let me review what it says. It says I shift the bottom 2 rows up 1 level and put the top row at the bottom. So it looks like this. Question, what is the relationship between the determinant of A and the determinant of B? Yes,
Opposites.
I think so. They do the same.
I find it's. One.
You did 2 swaps. Right? First swap, and there's a number of ways to do it. I split R1 and R3. So now the determinant is minus. Right? Because what I've done is I've swapped 2 rows. Everybody remember that when I swap 2 rows, it changes the sign? But I'm not there yet because I need to have R1 on the bottom. I've got this, but R2 and R3 are out of place, so I've got to swap them. Now it's back to place. So they should be exactly the same. There are degrees of getting this wrong. You were just in the middle of getting it wrong, right? Because you said they're opposite signs, that's ballpark. If you had said the relationship is the determinant B is 10 times the determinant A, that's a bigger problem.
Yeah,
Right. But it has to be either, when you're swapping rows around, it either has to be the same determinant or minus, right? Is that clear what happened here? Questions? Yes.
Did you give me your 20-second definition of linear inheritance?
Linearly, yeah, so the best, so if what you're trying to do is write a definition down, a set of vectors. By the way, this can be, so it doesn't matter. Is linearly independent. Yeah. Any equation. C1, BI1, plus C2, BI2, C10, BI10, zero vector. With CI reals, BIJ, set vectors. Then C1, C2. So whenever you have a linear combination of vectors out of the set equaling zero, the weights all have to be zero. That's it. So that's in English. If you have any set of vectors, you have any linear combination of those vectors, any finite linear combination of those vectors that equals zero vector, all the weights have to be zero. That's what it means to begin with.
And so would you accept that? Like if I said, if there is a linear combination that includes non-zero numbers for coefficients and it equals zero, then it's linearly dependent. Therefore, there has to be linearly, like all the coefficients must equal zero.
Well, so if you carefully define linearly dependent
Right.
and say linearly independent is not linearly dependent, I would accept that as long as you're correct about your linearly dependent.
Okay.
I think it's easier to do this, and it's easier with a finite. So if you have a finite set of vectors, the only reason I do a potentially infinite set is to distinguish. It doesn't matter whether the set is infinite or finite. You're always doing a finite sum. So if I had B1, B2, Bn are linearly independent. If any equation form C1, D1, C2, D2, Cn, Dn, zero vector. Implies C1, C2, Cn.
Yes. That.
Yes.
Whatever way.
Oh, well, polynomials are that, right? So for example, by this notation, I mean all polynomials. I don't think really is. And the reason for this is, if you write a finite sum out of this, there has to be some largest degree of term. So you have C1 plus C2x plus C between X squared plus, I should have started with C zero without an plus, C n minus and plus one, X n equals 0. Think of it this way, right? This doesn't mean for some X, this means every single X, right? So play match games. This is just like any of y'all in here, differential equations. Okay, well, you might have seen some before, but sort of play a match game, right? C1 is 0, C2 is 0, C3 is 0, and so forth. If you wanted to go through this carefully, so all the C's have to be 0. When you plug in X equals 0, then you get C1 equals 0. Agree? And so now what you have is C2X, C3, X squared, C2 plus 1. And now you can plug in other stuff, but it gets more complicated. You plug in 1, and you now get C1 plus C2 plus, or I'm sorry, C2 plus C3. You can plug in 2, or you can plug in -1, C2 minus C2 plus C3 minus C4 plus minus 1 n plus 1 n equals 0, and you can put in 2, and actually you can just plug in enough numbers until how many variables do we have? N minus 1. So you can plug in, actually it might be easier, so we don't have to worry about the minus sign. We'll plug in 2 here. To n, n plus 1. 3 C2 plus 9 C3. You just do this in plus 1 times, and now you've got what? Or you've got n unknowns, do this n times and n variables, and then show that all the CIs are 0. But I'm okay in this class. They play the match game. This is true for every value of X. And actually, I'm sure I can think of a shortcut. Put my mind to it for a moment. How you can do this, but think of any polynomial as being represented uniquely as powers of X, right? I mean, there's no other way to write that particular polynomial. And there's no other way to write 0 polynomial other than 0 plus 0x plus 0x squared and so forth. And so that gives the linear independence here, because if this polynomial is equal to 0 plus 0x plus 0x squared and so forth, then all the coefficients are 0. Right? But that's it. Yeah, and the span is clearly all polynomials, because any polynomial you could ever come up with, by definition, is a linear combination of 500 million things. That's what you all remember doing power series when we count 2. Yeah. But you remember there are all these things called power series, so like polynomials that somebody gave some bad drugs to and they just go on forever, right? Power series are not in the span of this, because the span is only finite sums, right? And so you have a power series like 1 plus x squared plus x cubed. You know, you look at these, they go on forever. Even though it looks like it's made up of those things, it's an infinite sum, and so it's not in the span of that.
There's not like, if it was like all polynomials to degree 3, it's only like 10x squared. But it's been,
What's in that?
like it was all polynomials to degree 3, I think the highest degree was x squared. But that's impossible.
Oh, right, you're talking about that. That's right. So I think the problem you're talking about is I gave you 3 polynomials, one of degree 0, one of degree 1, one of degree 2. I said these are polynomials of P3. no way that's fancy, right? Because there's no way to get an execute that. That's right. So, and you know that P three has dimension 4, right? You had 3 linearly independent elements. All you gotta do is add any element that has a cubic term. It's not 0. And that'll be, that's how. So the answer to that one about how do you, grow it to a basis has infinitely many answers. But what you do need in any correct answer is you need that polynomial to be genuine and cubic. You need it to have an x cubed term that's not 0. Yes.
However, it is a vector space within P three. Even if it's, or P four, even
Oh, you
though
mean
it's
the one,
degree.
the span of just those 3?
Right.
Yeah, it's a subspace. It's a 3-dimensional subspace in that 4-dimensional space. That's right. Other questions?
Yeah, you're referring to the,
Maybe I am.
you did work it out. real quick.
Yeah, sure.
That's what I said, in there.
All right, see you. Okay, so you have this set the. What is the subject? One. Okay, first explain what this is. See what. So suppose it's the 0 polynomial, 0 plus 0 equals 0 squared. So let me kind of regather some stuff. This is actually A plus B plus 8C. You okay with that? Yeah, all it is kind of group the stuff together, right? So maybe I put a vector there to emphasize the 0 polynomial, right? So this means that A plus B plus 8C is 0, and it means 2B is 0, and it means minus 3C is 0, right? What this immediately means that B and C are 0. Right? And once I've got that, I've totally got it. Because if B and C are 0, this means that A is. So the set's linearly independent. So the way I would finish this off, because it says expand this to a basis of P3 and justify. I know that P3 has one basis, 1x, x squared, x cubed, right? So it's dimension 4. I've got a linearly independent set. 1 plus 2x, and 8 minus 3x squared. All you need is an x cubed term, right? Because what you need is if you have, I'll just put an x cubed there. Now you've got a set of 4 linearly, right? So that has to be a basis. And also, it's fairly easy to see this 4 spans as well. Right? So, and actually, x cubed is unique. You could have put any cubic polynomial that has that's really cubic, right? You can't put a 0 in front of the x cubed, but like you could put 10x cubed plus 5x squared minus 6x squared. That would be another way to do it. Other questions? You got here early. Did you finish your lab?
I got so fast that we just sped through it so quick. I was fast so bad. I have a question about this. I did it a different way. I can't remember if I got credit. I can check this. But I took those elements in that those set of vectors and I basically turned it into a matrix and I said that because of the pivot in every column or whatever. Is that, can I do that? Or
Yeah, what you're doing essentially is you're doing linear transplation. I mean, I would give you a lot of latitude probably on a test, on a quiz, you know, I might want you to explain it more, but yeah, I mean, that's essentially what you're doing. Because this vector space is really isomorphic to R4, right? So you can think of if you think of the polynomials, you think of one as E1 and X is E2 and so forth, then you can do that kind of thing, you make a matrix out of it.
you gave me credit for that.
Was it?
The grader did give me credit for that, so I guess it does work.
They did give you credit? Okay, good. Which was 15. Other questions?
I had a question for Tom Friday. Is email the best way to ask you about some of these topics?
Yeah, I sometimes I'll try to get back to you. I've got a lot of meetings going on Thursday and things, but I should be able to get back to you.
I don't think well, I'll do it just like worst case scenario, but I just can't figure it out.
Yeah, just email. I'm sure. I just didn't want to make any guarantees, but I'm pretty sure I'll get back to you pretty quick. I hope. And I'll be in Friday comfortably before 6 in the morning. So,
Okay, before 6?
oh yeah.
So I usually up by 5:30, so will you be there somewhere?
Your problem will be the building will likely be locked, so you'll have to call my office phone or something like that. You can get in.
Okay,
But yeah, I'll be.
thank you for your time so much.
No problem.
Nice to see you Friday.
Sure. What's it now? So what was that? Did you say you had a question or?
Yeah, I was supposed to do it. Yes.
All right, so we'll just take your time. So it's what the intervals. Showing the interval functions of linear.
Yes.
Okay. Were you in class today? Right, so did you understand what I was talking about when we did that I vector T? So which one is this now? Fall 2022, what's the number? Fall 2022. Or. Okay, so. I can't quite hear you. I'm having a stupid thing. I'm hearing it. It's the PK is this vector space, all of these are careless. And. Oh, okay, so. F. And so this is like the one we did in class today, except now I'm integrating from 1 to X instead of from 0 to X. And that might get subtle difference. Show F as a linear transformation. To show that this function is a linear transformation, you just have to show that it respects the zones and it respects the scalar one. So you look at F of P of X, well, let's say F of X plus P of X. So these are both polynomials. It's the end of 1 X. And you can split up intervals. Then very polynomial here. Okay. That's respect for the division, right? After the sun is after the separate. And we also have to have relative F of C F of X. Equal from 1 to X of C F P P. I can pull a C out. This is C. So I can pull constants out as well. So there you go. It's linear transformation. And part B, it said it's F 1 to 1, it's F on to explain. Well, I think that F is 1 to 9, I think. Let's test my hypothesis here. Mean something to be 1 to 1, it means when you put in 2 different inputs between So how do we test this? Suppose that the output, when I put in little f, is the same as the output when I put in little g. I need to come to the conclusion that f and g are the same. That's what it means with 1 to 1. Same output means that you have the same, right? Well, suppose we have this, so the integral of 1 to x. The integral of 1 to x. These two intervals are the same. So next step, take the derivative, be the fundamental theorem of calculus. The derivative of this is f of x, derivative of this is g of x. So same outputs means same input. So it's 1 to 1.
Also use that to do the onto.
Onto you have to show that every polynomial of degree n plus 1 is not lonely. There's some polynomial in front of it. But I don't think it's going to be onto. And here's why. So those f right is zero 1 to x of a0 plus a1 b plus a2 t squared. And this output should be a polynomial of degree n plus 1, right? So this is a0 t plus 1/2 a1 t squared plus 1/3 a1 t cubed. I'm sorry, a2 t cubed. 1 over e plus 1 a n plus 1. Actually, minus a0 minus this might be a little bit difficult to see, but can you tell me, so is it possible to write every polynomial of degree n plus 1 in this form? Let me rewrite this by the way. This is a0 times x minus 1. This 1/2 a1 squared minus 1. 1/3 a2 is x cubed. See, I haven't. Okay. So this is in. Can you show me polynomial, then you cannot possibly write it this point? I'll give you two. I'll give you two polynomials. You can't write it. Actually, there's three of them. None of these polynomials. Do you know why? Suppose that this was equal to 1 or x squared. If this polynomial could be written in this form, what happens when you plug in 1 to this polynomial? It's big math. What happens when you plug in 1? When you plug in 1 for x? All these terms drop out. You remember that? So when you plug in 1 for x, this you get C. Right? What happens when you plug in 1 to 1? You do not get 0. There's no way you can write 1 in this form. It can't be done. Right? You can't write x in this form because when you plug in 1 for x, you don't get 0. So there's lots of poly, so it's not onto it because you don't get every possible polynomial. That was a little back on. I guess that was kind of being problem, but anyway, I didn't.
Yeah, it was a lot of sense, but I think
Well, and actually, the connection with what we had yesterday is the polynomials we got there, it was easier to see. The polynomials we got there were the ones that you could plug in 0 to, and you got 0. But now, these are the ones you plug in 1 to, and you get 0.
Almost said like, that's if it works on and is it on to.
Yeah, so this one right here is 1 to 1, but it's not on. By the way, we didn't even have to rewrite this because I didn't think about this that well. But this thing at the end of the day is a polynomial, right? Whatever I get here is a polynomial. Notice, plug in 1 for x, you get the interval from 1 to 1. So whatever this polynomial is has to have this property when you plug in 1, you get 0. 1 itself doesn't have this property, so it's not on.